Hello, and welcome to our session on increasing trust and transparency in AI. This is focusing on executives. My name is Michael Hind, and I work for IBM Research in New York. And we're joined by Ninjo Sarkar and Sudesh Krishnamurti. And they're both in the Data and AI organization. We're going to be talking about this topic in basically three parts. The first part I will cover, and it will talk about how research is looking at this problem of increasing trust and transparency from the point of view of an executive. There's another session we did focusing on developers, which covers open source toolkits in a bit more detail. And then I'll hand it over to Ninja. We'll talk about our product in this space, OpenScale, which will take some of the ideas from research and make them hardened and ready for enterprises. And then Sudesh will show an actual demo of OpenScale. Feel free to ask questions as we go along, and we'll try to answer them. So next slide, please. So as I mentioned earlier, IBM Research works very closely with product teams. And what you see in the picture here are some researchers and product folks. I'll let you try to figure out who are the researchers and who are the product people. But the point here is I'm showing you some stuff in a second about what research has been doing. And some of this that gets proven and validated with customers, we actually move into products, which you'll hear shortly from Ninjo and Sudesh. Next slide. So when we talk about the space of trust and transparency, there's a lot going on. It's not simply a technical problem that one company can solve. There's a lot of consortiums around this space from all different perspectives, either from like the EU higher expert group on AI, where IBM had the sole representative from a company, or a partnership on AI, where IBM was one of the founding members, or working with standards bodies such as NIST in the US, IEEE, and others, or in open source, the Linux Foundation, where IBM is a co-chair, and so on. There's many activities, many groups working in this space, and it's important to be plugged into all the different activities so you know what's happening. Next slide. So drilling down, when people talk about AI, they often focus a lot on accuracy, how accurate is the model. And that's important, and it's particularly important in high-stakes decision situations, such as applying for credit in the finance situation, or employment, or admissions to higher universities, or in criminal justice. Next slide. And in those situations, you want to certainly have accurate models, but you also want to have models that you can trust. And what we have on this slide is a few concerns that you would have beyond accuracy that you would need to be able to trust the model. And they are, is the model fair, or is it not biased? Is it explainable? Is it robust to adversarial attacks? And what's the level of transparency or governance I can have on the development of the model? So what we saw at IBM was a lot of people working in all these fields. They're huge communities. They have their own workshops and so on, and society caring about these problems. But there was a gap between the two. And we tried to accelerate closing that gap by creating open source toolkits. And the idea was these toolkits would capture what the science has done in actual real code in a common code base, so that people can actually start playing with it and giving feedback to the scientists on whether they're solving their problems or not. So back about 2.5 years ago, we released the Adversarial Robustness 360 toolkit. It's open source toolkit in Python. And then a bit later, we released Fairness 360, another open source toolkit. And then finally, Explainability 360 was around last year. All these three toolkits are open source. They're available, written in Python, and people can play with the ideas. More recently, we released a website called Factsheets 360, which talks about the transparency and governance. I'm going to cover some of that in the rest of this talk. The three toolkits are also, there was a lot of significant pull from other companies that would like to have them in an open governance situation. So IBM recently donated them to the Linux Foundation. We're very much involved, certainly in the project, probably more so than before, but it's now under open governance. And it's also available in IBM's Cloud Pak for Data offering, the three packages. So I'm going to focus on governance and transparency in this talk. If you're interested in the other three topics, I suggest you look at the other video that's the same title, but focusing on developers. Okay, next slide, please. So transparency and governance are related, but they're not exactly the same thing. So transparency is looking at the concern of, I have an AI system, and I'm worried about whether it's being used appropriately or not, right? Maybe it's approving credit in a loan situation, and I'm wondering if it was really trained on the right kinds of people. Maybe it's not necessarily people like me, and is it really appropriate? So the consumer wants to know something about how the system was built. And, an analogy that's often used is something like nutritional labels on packaged foods tells you something about how the packaged food was created, but doesn't give you all the details of otherwise the company would be out of business. So that's what AI transparency is about. Governance is about transparency and more, right? It's saying, can we document how things are built? Maybe because we have consumers or regulators who care about it, or maybe we just care about it within our enterprise. And then can we control it? Can we have specify actionable policies that say things like, please measure bias throughout the life cycle and make sure it's a certain value. And then finally, what you'll see is when you have all this information, you like to make it available to all stakeholders so that they can actually benefit from the information. And I'll also illustrate that in the next few slides. Next slide, please. Okay, so just focusing on transparency for a second. The idea of having a transparent product is not new. It exists in many, many industries. And on the left is just some examples, right? I already mentioned nutritional labels for packaged foods. In a lot of countries, they're concerned about energy efficiency. So the top right there in blue is what the US does for major appliances. They have one bit of information: is this appliance energy efficient or not? And the lower is a similar idea, but just lower is a bond ratings, where you have consumers who want to buy bonds, and it's a question of whether or not can you give me some information about the riskiness of the bond? And that's why we have these rating agencies. So what's interesting in all these cases is you have more information than than you had, but they tailor it to what the consumer needs to know. In the cases of the one bit of information, someone decided. And so the question is, what would this be like? What would transparency be like for AI? Is it going to be one bit of information, yes or no? And our feeling was that it's too early right now to get down to one bit of information of whether something should be trusted or not. And so we wrote this paper that suggested possible ways of documenting. Next slide, please. Okay. So one of the things we spoke to a lot of customers, and this is getting more into the governance side, a lot of customers have this problem. They need to document how their models were built because they're often in regulated industries. You see this a lot in the financial industry, where they're regulated and they need to demonstrate to a regulator that they're building their model in a risk-free way, or as risk-free as possible. And what we heard was often data scientists were creating extensive documentation, sometimes hundreds of pages, writing down their procedures. And then we spoke to model, and we found out that a lot of the information that was being written down wasn't really useful to what they tried to do. They were trying to assess risk. So there was a big need in this space, and still is a big need, to be able to automate this as much as possible. The next slide, please. So we've written space. These are all available on our website. That's talking about improving transparency and also moving towards governance. Next slide. We also have this website that has a lot of information, some of which I'll talk about in a second. And so there's a lot more to say on that. People look at. Okay, I'm not seeing the next slide. Maybe some bandwidth issues. I apologize for that. Okay, so AI governance. As I mentioned before, this is similar to what I had before. There are these three parts. There's automated documentation aspect. There's specifying policies to be enforced, and then there's making information accessible to all stakeholders. This will be more clear in the next slide. Okay. So what we have on the left here is a typical life cycle of how AI is built. You've got your business owner who says, hey, I think we might be able to use an AI system to improve some process, make better recommendations. That business person will ask a data scientist to go off and experiment and say, here's the problem. Can you produce a model for that? And then once the data scientist is done, that typically goes to some kind of testing or validation function that's going to test the model and poke at it and essentially look for risk. Sort of ascertain where will it be to the enterprise. And then finally, if the model is deployed, there's an operations engineer who's going to monitor model with something like OpenScale, which we'll hear about shortly, and be able to detect when something is going bad or not. So each of these people have facts about what they've done. Even the business owner who's not technical has facts about what this model's purpose was and maybe what kind of rules need to be applied during the development of the process. Next slide. Next animation. So what we want to do is capture all these facts in some kind of central repository and then make them available to people in the forms of reports or queries. And I'll show you an example of that. These people can be those in the life cycle, or they could be other people like a chief risk officer who wants to monitor how my development processes are going. Are there some that work better than others? Can I learn from them? Next slide. Okay, so here's an example. This comes right from our website. And of course, there's a lot more information if we scroll down. This is just a screenshot. The idea is this example is an example fact sheet. It's for mortgage evaluation. It comes from a public data set from the U.S. government on home mortgages. And the idea is we built a model for this, and we captured the information similar to what I showed you in the previous slide. And on the top, we show this idea of a template. And the idea is you've collected all this facts, but maybe not every person is interested in all those facts. So you kind of have a filter on those facts depending on what each person wants to see. Next slide. Here's another snippet of the same fact sheet. And what I'm focusing on here is the validator. So we're in the validation stage, and the validator is looking at the model the data scientist gave her. And she's actually measuring different things. She's measuring fairness. She's measuring some level of explainability, some level of robustness to adversaries, and some quality metrics there. And these are just metrics that come out of tools such as OpenScale, and they're all recorded and they can be rendered in this this web page here. Next slide. What this shows is the same kind of information with those four broad categories, but it's showing them at different points in the life cycle. So it's one model, but on the second column that says data scientist, that's showing that what were the values when the data scientist tested it with their test data. The third column is what are the values when the validator tested it with the validator's data. And then the fourth one is what something like OpenScale would measure in terms of real information. And this could be valued to all people in the life cycle, but also someone like a chief risk officer who could say, wait a minute, I expect things to go down as I get closer to real traffic. But if things are going up or going down dramatically, then maybe when our process needs to be improved, we need better ways of testing things, for example. Next slide. Here's another example. It's also on the website. This shows the difference between two different models. So in the financial industry, quite often a validator is going to do a challenge model. A challenge model basically says, I got a model from a data scientist, and let's say it has 100 features and it's a neural net. There's a lot of risk in that because it's a pretty complicated model. I wonder if I could solve the same problem with a very simple model, maybe a linear model with 5 features. So the validator often creates this challenge model, a very simple model, to see how much worse it is than a data scientist model. If it's close to the data scientist model, then often the validator tells the data scientist, you kind of overthought this. Please see if you can simplify your model so that we have less risk. And this illustrates this kind of comparison. Next slide. So just to wrap up, there are these 4 websites, all available from my webpage. All these URLs here. I focused on the right column, which is Fact Sheets 360. IBM just announced yesterday that we are productizing the Fact Sheets concept. So you'll be seeing that soon in Cloud Pak for Data. And the 3 on the left are our open source toolboxes that you can play with. They're geared towards data scientists who want to play in this space and learn about things. What you'll hear very shortly is you'll hear about IBM's product, which is basically taking the best of these ideas and putting into an enterprise-ready product called OpenScale. So I'll turn it over to India to pick up on that thread.
Thanks, Mike. Good afternoon, everyone. My name is Anindo, and I'm going to talk about OpenScale. So what you heard so far is the work done by IBM Research, and most of this work is made available to open source and valuable for data scientists to perform trust and transparency on their models at an individual level. But when it comes to actual business world, these efforts are rather limited by the ability to scale across entire organizations. In the real world, to make it useful, you need the power of automation and to drive the productivity and adoption of your models. So Watson OpenScale is an offering from IBM to exactly meet that requirement. So in this section, we will see how OpenScale takes these concepts of trust and transparency and how it works, and then followed by a quick demo of the product itself. But before we start, let us look at the overall ecosystem in which OpenScale operates. First, OpenScale is open by design, which implies that OpenScale can track and monitor the trust and transparency parameters of the model, irrespective of how it is built and where it is deployed, either using IBM tools and services or using any third-party tools and services. Now, during build time, the data scientists can use any popular open source framework, such as, say, scikit-learn, TensorFlow, Keras, Caffe, etc., to build their models and train those models, and at the same time get access to the rich tool set of OpenScale to do bias detection, to do accuracy monitoring, to do explainability of those models. Now, thereafter, operations team can take over those models and manage them and deploy them using their own DevOps tool sets in their existing runtime environments or maybe on their preferred cloud vendor environments. And finally, the business users will be able to manage and trace the individual AI workflow outcomes for auditing and regulatory requirements. Now, at a very high level, OpenScale has 3 key objectives. The first and foremost is to ensure that the model adheres to the compliance guidelines, the regulatory guidelines that are there in place. And this is done by constantly monitoring the deployed model in production at runtime, and then detecting any bias that is shown by the model and explain the decisions of the model for in a plain, simple language that humans can understand. Now, then, followed by that, it ensures that the models deployed are resilient over a period of time while business situation and underlying business conditions change. And this is done by doing a drift detection on the model itself. And finally, it ensures that the models deployed are aligned with the business KPIs in place, and any deviations from those business KPIs are automatically flagged off. And this is done by a correlation analysis of the business performance data with the model accuracy data. Now, in the next few slides, we will look into these 4 aspects of trust and transparency that Mike talked about, and we will see how those are incorporated in OpenScale product. So first, let's talk about bias and fairness. So to calculate bias, OpenScale monitors deployed models in production at runtime. The transactions, it captures the transactions received by the model, and it also captures the responses given by the model. Now, for bias detection, it divides the feature into two groups. One is called a monitored group. This is the group which is likely to be discriminated against. In our diagram, the blue box on the right. And the rest of the group is the reference group, which is unlikely to have any bias. In our case, the green box on the left. Now, bias is calculated as a ratio of favorable outcomes received by the monitored group to that of the reference group. In addition to this, there are a lot of value-added capabilities like auto recommendation of likely biased candidates in the feature set, or auto debiasing of biased responses without the need of doing any kind of retraining of the model itself. Now, OpenScale, to identify bias, applies something called perturbation analysis. Now, in this process, synthetic transactions are created. So for any inbound transactions in the monitored group, if it receives an unfavorable outcome, a synthetic transaction of the same transaction, but with that monitored group replaced with a reference group value, will be submitted. And the model behavior will be observed. If the model behavior changes from an unfavorable response to a favorable response, the model will be assumed to be having biased properties. So for example, let's say if a female candidate loan application gets rejected, then immediately that'll trigger a synthetic application from a male candidate with exactly the same application parameters and other features. And if the model behavior changes from unfair to fair, then the model would be assumed as having a bias. Now, to prevent proliferation of perturbed transactions, OpenScale also applies something called an optimization algorithm, which minimizes the number of perturbed transactions that are required to identify the bias. Now, using this combination of actual transaction and the perturbed transaction, OpenScale then creates an internal bias detection model, which will be able to look at a payload data and predict whether that payload data is likely to receive a fair outcome or an unfair outcome. And if it is likely to receive an unfair outcome, then debias it automatically and produce that result as well. Let us now move to explainability. Now, broadly, there are two ways to perform explanations of models. One is called LIME, and the other is called contrastive. Now, LIME is an open source algorithm. It stands for Local Interpretable Model Agnostic Explanation. Now, local implies that the explanation being provided holds good in close proximity of the instance being predicted. Interpretable means that the explanation provided is understood by human beings in plain simple form, and model agnostic means that the internal workings of the model should not matter, and we should not need to peek inside the internal workings of the model to perform the explanation. Rather, we should be able to explain it just by looking the behavior of the model from outside. Now, compared to that, contrastive algorithms is an IBM proprietary algorithm, and it tells us the maximum variance allowed in the feature set for the same outcome to hold true, or the minimum variance that is required in the feature set for an alternate outcome. Now, OpenScale provides both LIME and contrastive explanations. As part of LIME, it will tell us what are the factors that influenced the decision and to which extent. And as part of the contrastive, it'll provide what-if scenarios to explore how much variance is allowed for the current outcome and what kind of variance should be there for an alternate outcome. For example, in the local for explanation, a loan is rejected, and the explanation will be able to tell us that the loan got denied because of existing loans, a low savings rate, and the fact that the applicant is residing in a rented accommodation. Whereas there could be other factors like salary or employment duration, etc., which favorably contributed to the decision, but their factors were not nearly as enough to outweigh the negative factors. Compared to that, contrastive explanation will tell us that had the applicant had one less outstanding loan, or 25K of more savings, or had lived in a owned house instead of a rental accommodation, then the loan probably would have been approved. Now, there could be many, many use cases of explainable AI, but the key ones are at build time for data scientists to do debugging and understand the behavior of the models and ensuring that the model is behaving the way it is expected to. And for the end consumer of the decision of the model, provide an explanation of why the decision was made and what are the factors that contributed positively and negatively to that decision. And finally, for the business owner to ensure that the model adheres to the compliance and regulatory requirements in place. Let us now move to drift. Now, we spend a lot of time training the model for days and weeks and making sure that the model behaves accurately in production. However, the model that is working well today may not do so in future. A good model that has been developed, trained, validated, and deployed in production is always susceptible to drift over time as the underlying business situations change. Now, a drop in either model accuracy or the data consistency will result in a negative impact in business, and that has to be corrected by retraining the model. Now, drifts can be thought of as belonging to two different categories. One would be accuracy drift or model drift, in which the model accuracy drifts over time. The other would be a data drift, which implies that the underlying data or the payload data is deviating from the data set that was used during training sessions. And that is a data consistency drift. Now, OpenScale will measure both data drift and accuracy drift. As part of the accuracy drift, however, OpenScale does not need labeled ground truth data, as it may be really inconvenient to get such data in real time for measurement purposes. So what OpenScale does, it uses the training data used during evaluation for measuring accuracy drift. If the payload data deviates from the training data, then it is considered that the model will be drifting away. Now, data distribution drift can be of two types at a very high level. One is a feature outlier, and the other is called feature imbalance. Now, feature outliers, as the name suggests, are rare occurrences of feature values. Say, for example, 80 years of age, which was not present in my training data, or say 500K of salary at an age of 25, not present in my training data. On the other hand, feature imbalance is a distribution disparity between the payload data and the training data. Example could be age 60 is appearing too frequently in the payload data, or a salary of 100K at age 50 or plus is appearing too frequently in the payload data, and that was not the case in the training data. So Watson OpenScale analyzes each transaction of the payload and compares the consistency of the payload with that of the training data, and compares it with the constraints that it learned from the training data. If any of those constraints are violated, then it tags that transaction as showing properties of drift. And based on the behavior of the drift, it also does a clustering of the transactions into different types of buckets, like those showing no symptoms of drift, those showing only data drift properties, those showing model drift attributes, and those showing both data and model drift properties. So finally, let's move on to accuracy or quality measurements of a model. Now, like the previous matrices, there's no single way to measure accuracy, as you know. There are many ways to measure accuracy, and depending on the scenario you're likely to use one metric more over the others. But what is important to note is that if payload data is available, labeled ground truth data is available, then OpenScale will automatically calculate all these accuracy matrices and make it available for business users to use. But this is just a technical measurement. For business users, what matters more is whether the business KPIs are in alignment with this measurement. To ensure that, OpenScale can automatically correlate business performance with the model matrices, and any deviations are automatically flagged out. And it can do so automatically if the ground truth data is, and the business KPI data is uploaded into the system. So now, before I conclude, to wrap up, let me say that OpenScale measures on all major operations around AI, leveraging the most common open source frameworks and runtimes. To increase the confidence of that AI for business users, OpenScale can track and monitor business outcomes, enable business users to adapt to the AI in the way they want, and enables compliance and regulations on governance on the AI in production. Now, in the area of automation, OpenScale automatically detects and mitigates bias in the model output without affecting the actual model that is deployed or its original outcome. And finally, OpenScale is open by design, which means you can monitor and optimize the models in third-party model serve engines or inside your enterprise firewalls or on infrastructure as a service providers serve engines. So with that, I'll conclude my session and hand over to Sudesh for a quick demo of the product. Over to you, Sudesh.
Thank you, Anindya. I'm going to continue from where Anindya left, basically show you a live demo of a scenario of a credit risk model showing OpenScale in action. So the model that we are taking is basically a credit risk model. The goal of the credit lender is to increase the loans. At the same time, they want to reduce the risk of giving loan to a wider variety of customers. And since they have to deal with a wider variety of customers, they have to use all kinds of data to arrive at these kinds of predictions. Now, what OpenScale will do is basically, make sure that even if the models are in a black box, basically come up with, the explanations of why a particular loan was denied or why a particular loan was approved. So let's take a quick look at the OpenScale in action. So here, what you see is a dashboard which shows all the models that are deployed in multiple providers. Now, these machine learning providers could be, Azure ML, or it could be Amazon, or it could be other third-party machine learning providers. These models today are hosted on Watson Machine Learning. So you see here, I have three models basically that are running. One of the model is in production as shown by the tag. One of the model is in pre-production and is approved, and one of the model is in pre-production. Right? And I can see that the model monitors for different parameters. One is quality, fairness, and drift. I can actually look at more details of this by looking at a detailed dashboard. This is an operational dashboard that kind of shows various attributes of the model. So here we see that the model monitors for fairness, for various aspects of quality, and as well as the drift. So let's look at fairness. As Anindya explained, there are few monitors that we can put on fairness. One being, let's say in this case, one being the gender and other being the age. So what we want to monitor is whether the loan applicants are biased for either for gender or for age. In this case, we can actually add other kinds of monitors based on the scenario or based on the business rules. So let's take a look at look at details of this model. We can see that the fairness is 58%. So if we want to actually drill down why the fairness is only at 58%, we can go and investigate this. So here we want to actually set up some kind of a fairness score, which is and also a threshold for the fairness that is acceptable to us. In this case, the red line is actually the fairness threshold, which is set at 98%. So anything less than 98%, we want to term that transaction as biased. So you see here that the green line shows that these transactions are biased here. Now we can look at more details how we arrived at a fairness score, as well as how we define a threshold. So here you see in this that we are monitoring the gender, and we are looking at looking at how we calculated the fairness score. So here you see that when the people applied for loan, if their gender was male, they were 49%. They received 49% favorable outcomes, whereas in case when gender was female, they received only 38% favorable outcomes. So the biasness was 10%. The way we arrived at a fairness score is basically having the ratio of favorable outcomes of the monitored group. Remember, in this case, the monitored group is female, divided by the reference group. In this case, that was 49, right, of the male reference here. Right? So we arrive at we kind of arrive at the fairness score by this calculation, and this much was the bias. So let's look at let's further investigate this. Why is there a bias? So we have various parameters. For example, we can look at the training data set if it was available for this model. So you can see that for gender, we can see that there was more number of male applicants than the female applicants. You see, there were only this many female applicants compared to the male. So one of the reasons could be the training data was available more for male reference groups versus the female groups. We can also look at these debiased endpoints. What this means is if we want to make sure that the transaction is not biased, what OpenScale will do for us is basically switch the monitored parameter, in this case the gender, with the reference gender, and check the outcome. If the outcome was any different, then in that case the transaction is biased. So for example, in this case, if all other parameters being the same, like age of a person, salary of a person, and other attributes exactly being the same, and only gender changed the outcome of the transaction, that means the transaction was biased. We can there's no need for retraining the model. The OpenScale automatically does that, and it provides the API endpoint where people can then call that API endpoint. We can further investigate these transactions by looking at the actual payload information. So you see here, OpenScale will capture the details of the payload transactions. So let's take a look at one of these biased transactions where OpenScale is saying that transaction could be biased. So here is one transaction where it says it's a very risky transaction with 84% confidence, thereby indicating that the loan of this person be rejected. So let's look at why this particular loan was being rejected for this person. So what OpenScale will do is basically show you list of attributes that positively influence this outcome, or it negatively influence this outcome. So here are various attributes that positively influenced this outcome. So you see that this gender was a key in influencing this decision to be a risky transaction, thereby suggesting that the loan be rejected. And there are other parameters that also play part, and OpenScale actually finds out the weight of those parameters. We can further inspect this and go into a very detailed view of these transactions. And then this is here you see that there are various features that contributed to 84% confidence of the model predicting that this transaction is a risky transaction, thereby suggesting that loan be rejected. Whereas this is the transaction where OpenScale synthesized, and what it did is, with all other parameters being the same, that includes loan duration, credit history, loan amount, everything being the same, it just flips the monitored attribute, which is in this case gender, from female to male, and you see that the outcome of the loan changes to no risk at 61% confidence, thereby suggesting that loan can be approved. So this obviously indicates that there was a bias in the transaction. So what I just shown you is how you can detect a bias and also be able to explain why there was a bias in that particular transaction. So now let's look at the other attributes that OpenScale monitors. For example, let me just open the details. Let's go into the second area, which is basically the quality as well as the drift. So here there were some quality issues in the transaction. We can go and look at the details of the quality issues. So we can look at what was the accuracy of the model. So it gives you details, and based on the transaction, you just get plotted an hourly plot for several weeks. Now there is, at the same time, we see that there is this drift, which basically indicates that there is a drop in accuracy of the model gradually. So what we can do is basically identify if there was a drop in accuracy of the transaction over a period of time, and these could be for various reasons. This could be either because of either the change in the data that is coming in, or it could be change in the concept of the transactions. So let's take a look at the transactions that were responsible for drop in accuracy. So I can see that these are some of these transactions that resulted in drop in accuracy of the model. Now, not only that we would get the reason for drop in transactions, but we'll also get the actual features that were responsible for drop in accuracy. For example, in this case, the age was a primarily large influence on drop in accuracy here, and the other parameters also contributed to the drop in accuracy. And in the same way, like how I showed earlier, I can actually go into details of this transaction and look for explanation of these transactions, why there was drop in accuracy. And this could be again brought back and trained, and we can improve the accuracy of the model. So what I showed you is basically how you can monitor these machine learning models that are running on different machine learning providers, and you can monitor for the various aspects like quality, fairness, as well as drift, and get into the explanation of the transactions, which is now a requirement by a lot of regulators, and then go into continuously go and train the model so that you can reduce the risk and improve on the fairness. So this concludes my demo. So let me give it back to Anindya, and we will pose for any questions that you may have.